The common way for solving this kind of problems is to simply write down the first few numbers in the sequence and then, out of the sky, guess the pattern. But you might be asking, what if we couldn't guess the pattern? What if the problem is more complicated than this? We would like to find a systematic way for solving this type of problems. One issue we're facing is that there are multiple variables in this problem, A0, A1, A2, etc., and we should solve for all of them. What we would like to do is to transform this multivariable problem into a single variable one. What I mean is that if we're going to transform a of n to, say, a pickle, we would like to transform 2 times a of n minus 1 to a multiple of the same pickle. But how are we going to do this? We will use the following technique. Assume that we have the sequence 1, 3, 8, 5, etc. We will transform this sequence into a polynomial as seen here. This transformation has some useful properties which we're going to discuss. For example, assume this other sequence, which is basically the first sequence shifted once to the right, and the empty place is filled with 0. We can also call this sequence b of n minus 1. Minus 1 because it is shifted once to the right. The polynomial for this sequence is this. And if we notice, the second polynomial is just the first polynomial times x. So we conclude that if we shift a sequence once to the right, the polynomial is simply multiplied by x. Let's see the other properties of this transform. Say we have a sequence b of n with the polynomial b of x and c of n with the polynomial c of x. Then b of n plus c of n would have this polynomial. If we group out b's and c's, we would see that the result is b of x plus c of x. So if we add two sequences together, their polynomials are also added together. Another property. If we multiply b of n by a factor, which we will call k, then the polynomial would be as follows. We can group k out, and what remains is k times b of x. So if we multiply a sequence by k, the polynomial will also be multiplied by k. These two properties together are called linearity. One more property, and let me demonstrate it with two examples. Assume we have the sequence b of n equals 2 to the power of n. What is the polynomial for this sequence? The polynomial is this, and we would like to write it in simpler terms. So we would keep 1 and factor out 2x out of the other terms. What remains in the parentheses is b of x again. So now we can group b of x and then divide both sides by 1 minus 2x. So the polynomial b of x equals 1 divided by 1 minus 2x. Generally speaking, the polynomial for k to the power of n is 1 divided by 1 minus kx. Now consider the sequence of 1s. We will call this sequence u of n. It can be thought of the sequence of powers of 1, and so the polynomial for it would be equal to 1 divided by 1 minus x. Now that we have our weapons ready, we can attack the original problem. What we're going to do is to transform the original equation to an equation about polynomials, and then solve this equation to find a polynomial solution, and then see what sequence does this polynomial correspond to. Okay, so this is our equation. Let's write it down for the first few values of n. A of 0 equals 2 times 0 plus 1. A of 1 equals 2 times a of 0 plus 1. A of 2 equals 2 times a of 1 plus 1, and so on. we can see that this sequence is a of n minus 1, as we said earlier, which is multiplied by 2. And then we add to it a sequence of 1's, or u of n. And this sequence is equal to a of n. So this is the new form of our problem. Let's call the polynomial for a of n as a of x. Based on this box, we know that the polynomial for a of n minus 1 is equal to x a of x. Based on linearity, we know that the polynomial for 2 times a of n minus 1 equals 2 times x a of x. And based on this box, we know that the polynomial for u of n is 1 divided by 1 minus x. Again, based on linearity, we know that we can put a plus sign here. And since these two sequences are equal, we can conclude that these two polynomials are also equal. So this is our polynomial equation, and we're going to solve it now. We group the terms containing a of x, and then divide both sides by 1 minus 2x. So this is a of x, but we would like to write it in terms of the sum or difference of two simpler fractions. The systematic way for doing this is partial fraction decomposition, which I suggest you check it out later. But for simple cases like this, we can simply guess that the answer is 2 divided by 1 minus 2x minus 1 divided by 1 minus x. So this is our polynomial solution. We would now like to find the sequence which this polynomial corresponds to. As you remember, based on this box, 1 divided by 1 minus 2x corresponds to 2 to the power of n. It is multiplied by 2, so based on linearity, the sequence is also multiplied by 2. Then, 1 divided by 1 minus x, again based on the orange box, corresponds to u of n. And based on linearity, we can put a minus sign here. Now we know that a of x equals this polynomial on the right side. So we can conclude that a of n equals this sequence, which can be written simpler as 2 to the power of n plus 1 minus 1. And this is the promised answer.